Welcome to the solution video for question 1 of the modules of Morse circle of 3D stress and static failure theory. In question 1, the stress at a point is shown on the element. Determine the principal stresses and the absolute maximum shear stresses. So with any question, the first thing we want to do, we want to check what we have been given. We have a normal stress in the y direction, so this direction. We have our coordinate field here, given as 30 megapascal. We have also been given a normal stress in the z direction as 120 megapascals. And we also have a shear stress in the yz direction, given as 70 megapascals. So before we start looking into our Morse circle, just remember that principal stresses in a 3D stress element exist when the shear stress is equal to 0. So unlike our 2D stress element, there are 3 shear stresses instead of 1. So a normal stress along an axis is the principal stress when both shear stresses are 0. So the first thing we want to do, we want to check for any principal stresses. So check occurrence of any principal stresses. I'm just going to call that P. So normal stress in X, 0. And when I'm looking at my X, I'm then looking in my YZ plane. My shear stress in correlation to this, my XY component, 0. And then we want to check our shear stress in XZ as well, and it's also 0. That means because we have a normal stress and no shear stresses, that means this is actually a principal stress. But let's check in our Y and Z normal stresses as well, if we have any more. So 30, we have a shear stress in XY, again 0. Shear stress in YZ, we have 1, so 70, which means that this is not a principal stress. We have an occurrence of a shear stress. Same, we're going to do this in our normal stress Z, 120. Again, we're going to check our XZ, which again 0, and our YZ shear, which is 70. There we have it. These two are no principal stress. Because they have the occurrence of a shear stress. So now that we know this, we can actually figure out what plane we want to look at. We want to look at the YZ plane. So we want to look along our X into this element. I'm going to remove that in case that's confusing. And then we want to simplify this problem into a 2D element. So simplify. And our YZ plane. Now that we know we're going to look at that plane, let's go ahead and draw out our element. Going to have our Z stress. Put in my coordinates as well, my coordinate field, Z, Y, which means this is my Y. 30 megapascals. And then I have my positive shear stress in this plane. $70 megapascals. Now what I want to do, I want to start looking into my Moore circle. And if we recall from previous weeks, we start with our center point. C. C is just my average normal stress. My normal stress in Y plus my normal stress in Z divided by 2. We'll find that we have 120 plus 30 divided by 2, which is 75 megapascals. We're not going to worry too much about the reference point in this tutorial, mostly because we're not going to use it, not transforming any elements. So we then want to just find our radius. And our radius equals 2 square root our normal stress in Y minus our average stress squared plus our shear stress. In YZ direction. So you might have seen this part before in some solutions. They might give you another formula for this section here. You can use our Y minus our Z divided by 2 instead. So we can replace this section here with this, but because we already calculated the average, feel free to use that. It's up to you which one you want to use. You will end up with the same value, obviously. So let's just put our values in here. So 30 minus 75 squared plus 70 squared. Don't forget the squared in there as well. And we'll find that we have 83.217 megapascals. Now that I have my center point and my radius, I can go ahead and start sketching out my Moore circle. The center point is at 75. I have my principal stress 1 and my principal stress 2. So remember, in your Moore circle, at the moment, you might not already know which one is your maximum or minimum. We're going to have a third principal stress in there in order to draw out all 3 circles. So let's have a look before we start, what are the values of these principal stresses? So we know that our principal stress 1 is just going to be our center point plus the radius. 75 plus 83.217. We get 158. Right there, 158.217 megapascals. For our principal stress 2, simply just the center minus the radius. 75 minus 83.217. And it will be negative 8.22 megapascals. Now that we know that our principal stress 2 is located on the negative section of our Morse circle, I'm just going to go ahead and draw out my shear axis. What we want to do now, we want to find that third principal stress in order for us to find our other circles. So one thing that we can do, we can draw out the new element again. So our new element will then look something like this. That's the 3D element we're talking about. So we would have our 158.217, and then my negative 8.22. Look something like this. And what we can then go ahead and do, we would go and sketch the element by themselves. So my YZ plane, so my YZ plane, but using our principal stresses. Just a note here, I used this one as a positive direction, but I noted that it was negative. In here, I'm just simply going to notify this is in compression, and then I just write it out as such. 158.217. Then we want to look at our XY plane, which is this one here. We're just going to have our 158.217. And then we're going to look at our XZ plane, where we will just have our 8.22. So now that I have these three elements, basically this first one here correlates with the larger circle that I already drew. What I can then do, I can go in here and I can calculate the center point and the radius for my XY, and then I can do the same for my XZ. But we're going to go back to the top of the question, so in the beginning here, where we already found a principal stress. So we actually already know that our third principal stress is our normal stress in X, which is 0. So what I can do, I can in here then note out that this is my principal stress 3. Depending on the textbook, sometimes they don't like referring to them as principal stress 3. I'm just going to call this the same as my intersecting stress, int. And then we simply know that my radius for this smaller circle, so just remember your circles will always have the radius between either the maximum or the minimum normal stress and the intersecting circle. Sorry, the diameter. So my smaller circle here, if we look at our elements that we just drew out, we actually know that this is our xz plane. So recall our center point will be our average. So just by looking at this, we just have one stress. It's just this stress divided by 2. So we could have gone ahead and done all the calculations, but we knew that that stress, intersecting stress would be located there because we already found it. And then my last circle would then be located as such. Again, we can go ahead and look in the individual element, the x, y in here, and do the calculations for it, or we just go after the knowledge that our principal stress 1 would be located at the far right edge, and our principal stress 3, or our intersecting principal stress, will be located at 0, and we know the whole diameter then of this medium circle. So part of the question, we want to find the absolute maximum shear stress. So our absolute maximum shear stress will then be located down here. If our principal stresses have opposite signs, so plus and minus, then we can use the following formula, which is that our shear stress equals to our principal stress 1 minus our principal stress 2 divided by 2. All right, and as I mentioned before, imagine we drew our Moore circle. We found one of the smallest circles first, and I would have called this my principal stress 1. Just be careful with this formula. What it's referring to is our principal max minus the min. Just keep that in mind. It depends a little bit on the textbook you are using. So in this case, 158.217 minus 8.22 divided by 2. Is there a quicker way I could have figured this out? Yes, there is. I actually know that my absolute maximum shear stress is the same as my radius of that larger circle. So I actually calculated that already, just the radius, right? So if we go up, I know that it's going to be 83.217. So we can either go through all the different steps, or we can quite easily and fairly quickly solve it graphically using the Moore circle. And that sums up this question.